I assume that you don't know anything about odd-even merging. So first we'll be discussing odd-even merging technique, sequential algorithm. Then we'll be discussing that odd-even merging network, and then finally we'll be discussing about odd-even merging sorting network. Okay. First we'll discuss about sequential odd-even merge technique. Second, we'll be discussing odd-even merge network, and then finally sorting network. So this is a special purpose sorting network. Let us assume that A and B be the two sorted sequence, that A and B be two sorted sequence, and the problem is to merge these two sorted sequence. In odd-even merging technique, what it does, that it forms A1, A2 are the two disjoint sets. A1 contains the elements which are odd index, and A2 contains the elements which are even index. Similarly is the case of B, one and B2. Now, by odd-even merging technique, recursively merge A1, B1, and similarly A2, B2. Right? Say we have sequence A, sequence B. Now you get A1, B1, A2, B2. Right? You have the odd-even merging technique you are defining. Same thing you are defining here, odd-even merging technique recursively. You get D sequence, you get E sequence. Recursively you have done the odd-even merge of this, you get D sequence, you get E sequence. Agree? So let it be D. Now, if it is the case, then can I draw the conclusion B1 is the minimum? Huh? Sure. Can I draw the conclusion because minimum is either A1 or B1. right? So D1 is the minimum. That conclusion I can draw. Similarly, can I draw the conclusion that En is the maximum? Right? This too is clear to you. Now, second thing is that who is the second element, second smallest element? Any idea? D2 or U1, right? So this is the thing, this idea has been taken. So let us define C1 is D1, C2I is minimum of D I plus 1 EI, I is equals to 1, 2 onwards, and C2N is your EN. C2I plus 1, actually I have to write somewhere here also, because I have to tell who is the next one. So C2I plus 1 is maximum of DI plus 1 EI, I is 1, 2. Right. So that is the thing. So what is the strategy? What is the problem? Problem A is that given A and given B, two sorted sequences. I have taken the odd sequences which form A1. Odd sequence of B gives you B1. Even index elements form A2 and B2. Recursively you are merging A1, B1. You get the sequence D1, D2, Dn. Similarly you get the sequence E, E1, E2, En. Now C1 is D1, C2n is En, and C2i is defined by the minimum of Di plus 1 En, Ei, and C2i plus 1 is maximum of Di plus 1 Ei. Right? Now we have to prove that this gives the sorted sequence. That is the only thing. If we can prove this, you are happy. Right? So this obviously you don't have to prove, right? This is obvious. You don't have to prove this one. The only thing is that you have to prove this part. Now let us consider the subsequence of D that is D1, D2, Di plus 1. Let us consider this subsequence, and you will find it satisfies the criteria because this is recursively sorted. It satisfies this criteria. Now let us assume K of them belong to A sequence, right? Because D1, D2, Di plus 1, these sequences obtained from odd index subsequence of A and odd index subsequence of B. Agreed or not? So either we can assume that K of them belong to A sequence. What is A? A means A1 sequence, sorry. K1 of them belonging to A1 sequence. Then does it imply that I plus 1 minus K of them belongs to B1 sequence? Because total number of elements, agreed? Huh? Yes. Any ambiguity at any stage? Please tell me. K of this is assumption. K of them belong to this. It indicates that I plus 1 minus K of them belong to B sequence. Now, what does it mean? That K of them belong to A1 sequence means that A1, A3, A5 and so on. And you got, what is the index of this? 2k plus 1. Is it okay? If it is the case, then can I write how many of them, what should I write? Belong to original A sequence. Original A sequence. What should be the number here? Huh? Two? See, how many elements are here? Huh? K elements. Right? So, K elements. Are you sure?
Yes.
Sure, 100%. I have 3 elements here. How many elements are here? A1, A3 and A5.
K minus 1. K minus 1.
No, this index may be wrong, I don't know. Huh?
K minus 1.
Sure, 100%. You have 3 elements. In between, how many elements are there? How you are telling K?
K plus K minus 1. K is equal to A5 is 2K plus 1. So that index should be 2K minus 1.
This one, yes, maybe 2k minus 1. Maybe 2k minus 1. I am not talking about this part. I am taking that I have odd index elements, and between the odd index elements, how many even index elements are there?
K minus 1. K minus 1.
Right? That is k minus 1. So I can write it is k minus 1. Agree? So what is that? 2k minus 1? Because k minus 1 even index elements, k minus 1 even index elements, k elements are odd index elements, so total 2k minus 1 elements who are belonging to A sequence. Right? And they are because this is sorted. This is sorted. Agreed? Yes. Now, if it is the case, so can you tell me from here how many elements of them belonging to B sequence? How many odd index elements? I plus 1 minus k. And how many even index elements? I minus k. Then what is the total number of elements? 2i
Minus 1 minus 2.
2i plus 1 minus 2k. Right? That many elements belonging to B sequence. Right? What does it mean? 2k belonging to A sequence which is less than or equals to di plus 1. That many elements which is less than or equals to di plus 1. Is it okay? What we did? First we told that k elements of the B subsequence belonging to A1 sequence, it indicates the I plus 1 minus 1 elements belonging to B1 sequence. It indicates that 2k, it indicates the 2k minus 1 elements belonging to A sequence less than equals to di plus 1, and similarly 2i plus 1 minus 2k elements belonging to B sequence is less than di plus 1. Yes? Huh? And if I add these two, what I get? 2i 2i elements belonging to A and B less than equals to di plus 1. Right? Now, if C is the sorted sequence, so can I write C2i is less than or equal to di plus 1? Yes? Because by combining these two, I got 2i elements belonging to the combined A and B is less than or equal to di plus 1. And since C is the sorted sequence, that is the assumption, so C2i is less than or equal to di plus 1. Similarly, you can show C2i is less than or equal to ei. Just you start with ei 1 and you can derive this. Now let us consider the subsequence C1, C2, C3, C2i plus 1. Now this is sorted sequence, so I can write this is equals to this. Now let us assume that k of them belonging to A sequence. So I can write, this is assumption, I can write 2i plus 1 minus k of them belonging to B sequence. Because obviously that C has been obtained from A and B only. Now, can you tell me how many of them in that case from here of them belonging to A1 sequence? So this is the subsequence belonging to C. How many of them belonging to A1 sequence? Huh? K was. Now the K should either be even or odd. If it is odd, what is the value? And if it is even, so you will be writing K by 2 of them belonging to A1 if K is even, else K plus 1 by 2 of them belonging to A1. Agree? Now if it is the case, from here can I write something? How many of them belonging to B1 sequence? Now, assume that K is even. Assume first K is even. Otherwise, if K is odd, you have to do little manipulation that 2i plus 1 minus K divided by 2. Some manipulation for K equals to K is odd, what should be the change? Please write down. In both the case, if I get it, tell me, if I add these two, I get I plus 1 of them. So, belonging to K by 2 of them belonging to A1 subsequence, right? Which is less than equals to C2i plus 1, right? K by 2 of them belonging to A1 subsequence will be less than, because that is the thing I considered. Up to this, so I can write This is less than equals to C2i plus 1. Yes. Similarly, I can write this is less than equals to C2i plus 1. That means I plus one of them belonging to A1 union B1 or the merge of A1 A2, A1 B1 is less than equals to C2i plus 1. Agreed? And this gives you the condition that di plus 1 is less than equals to C2i plus 1. Because I plus 1 of them, di plus 1 is what? D is the sequence of A1 union B1. So di plus 1 is the first I plus 1 elements of this one. So I can write di plus 1 is less than equals to C2i plus 1. Similarly, you can write EI is less than equals to C2i plus 1. So combining these four equations, you can write that di plus 1 is minimum of, not di, Ci is C2i, because you know that C2i is less than equal to C2i plus 1, so from there you can write di plus 1 ei, and C2i plus 1 is maximum of di plus 1, right? Combining these four equations along with this, you can easily prove this. So the odd even merge technique correctly merges two sequence A and B and stores it in sequence C. This idea can be used to define the merging network. You have, suppose, n elements. These are A1, A2, A3, A4, B1, B2, B3, B4. And you have a network name is n by 2 cross n by 2 network odd even. Here input is all odd indexed and here input is all even indexed element. Right? So through some recursive technique you get the sequence D1, D2, D3, D4, Dn. You get D1, E2, En. So D1 is your C1, is C2n. And then D2 is compared with E1, you get C2, C3. D3 is compared with E2, you get C4, C5, you get D4 is compared with, you get C6, C7 and so on. I need a simple comparator. I need a processor which is nothing but a comparator. Now, the comparator is defined like this. You have an input A, you have input B, and output is minimum of A comma B, maximum of A comma B, right? So you need a comparator here which takes the input and gives the output like this, right? Now, if I have the two elements, I have two elements A and B. How many comparators you need to merge these two sequences? One comparator, and the structure is very simple. Now, if I have, say I need this later on. Now, you have A1, A2, B1, B2. These are the two sequences, each of size 2. You need, what should be the architecture? Right? Now, first problem is that I want to find out the number of comparators you need to merge the two sorted sequence each of size n. The number of comparators you need to merge two sequences each of size n. Tell me. N minus 1. So let's, are you sure? Huh?
N by 2 n plus n by 4 plus 2n by 2.
Tell me what is the number. First, how do you do that? You obtain a recurrence relation. What is the recurrence relation?
Every time it is half.
So tell me the recurrence relation now. Tell me what is the recurrence relation? Huh? 2n minus 1 is the number of processors you need. Okay. How did you get that?
N is equal to n by 2 plus n.
No, but how did you get it is 2n minus 1? Something has come to your mind based on some base, right? Basis. What is that basis?
Total outputs are
2n.
and for each of the two outputs that we get from processor, we require
Repair. How do you, because my feeling is that this type of problems you can easily solve through recurrence relation. I don't know other ways how you can do it. If you have any new idea, tell me, that will be useful for me. So if I consider C2n, because there are 2n elements, C2n is my comparator, is the number of comparators you need, then C2n can be written as Cn for this block For this block also you need again Cn. Agreed? So 2Cn plus, how many comparators you need? N minus 1 plus n minus 1, right? And you know a recurrence relation is valid if you put boundary condition also, right? So one way is that it is 1 if n equals to 1, if n is greater than 1. Now if it is the case, you check whether your recurrence relation is valid for this or not. That is n equals to 2. 2 into C1, C1 is 1, 2 into 1 is 2, plus 1, 3. You need the 3 comparators. Agreed? So this is the number of comparators you need. We will solve it later on. Now next one is the number of parallel steps you need. How many steps you need? Or what is the time complexity to merge two sorted sequences? Can you tell me now? T2n is equals to what? Tell me the recurrence relation first. Why 2Tn? These two halves, but they can do in parallel. Right? So I can write Tn plus 1 if n is greater than 1, 1 if n equals to 1. Right? Anything else I have to find out? One is number of comparators, another one is number of processors. These are the two things. Now I need to know the solution of these two. So I can write this one as Tn by 2 to the power k plus 1, 1, 1, 1. How many ones? K minus 1. Next time I will write Tn by 2 to the power 2 is equals to 1 plus 1 plus 1. Huh? Sure, k plus 1? K minus 1 is not there. No. K is there still or no? Sure. So if it is k plus 1, then it is k plus 2. Right? Because this is T1, T1 is 1, so k plus 2. So T2 and T2n is your k plus 2. So basically, if I have to write in terms of n, it is k plus 1. If I have to write in terms of n, then it is Kn is equal to k plus 1. But generally we are habituated with, while writing the time copy, we are habituated with n, not n2n. So if it is n, it is k plus 1. Now what about this solution? 2 times Cn plus n minus 1. Now tell me what I'll write. Is it okay? Can I write this? Can I write this? Yes or no? If it is that, then I can write 2 squared Cn by 2 plus n minus 2 plus n minus 1. So next time what I'll write? Tell me what I'll write here. 2 cube here, Cn by 4 here, n minus is it okay? So what happens to k times 2 to the power k plus 1 Cn by 2 to the power k n minus 2 to the power k So how many n's? K n's. Tell me. K plus 1. Where? This one? K plus 1. 2 to the power 0, 2 to the power 1. Yes. This is okay? So this gives you k plus 1 n plus 1. So you get C2n is k plus 1 n plus 1. So you tell me what is the value of Cn? K plus 1. K is your log n. the two sorted sequence, each of size n. What is the lower bound? 2n minus 1. It is m plus n minus 1. So it is 2n minus 1. So it is order n, and it is not, this is log square factor away from the lower bound. Agree? So this is your parallel odd even merging network. Now, can I use this merging network to sort the n elements? Let us assume that A1, A2, A3, A4, A5, A6, A7 and so on. These are the n elements. They are arbitrarily distributed and you want to sort it using odd even merging technique. The strategy is very simple. You assume that there are n by 2 groups, each of size 2, and this two size group is a two subsequences, each of them is sorted. That is, that I have defined that this is a group, this is another group, this is another group, this is another group, and so on. And we assume that there are two sequences, each of size 1. Okay. Now this is sorted, this sequence is sorted, this sequence is sorted. This sequence is sorted, this sequence is sorted. Yes. If it is the case, I can have one comparator to give me the sorted sequence. I can have another comparator. Right? So I get A1, new A1, new A2, new A3, new A4 and so on. Now you have n elements. These n elements have certain property that there are n by 2 sequences. N by 2 sequences, each sequence is of size 2 and they are sorted. Right? Now you divide again based on 4 elements, 4 elements, 4 elements. These two elements sorted, these two elements sorted. You can use odd even merging network to sort this. You can use the odd even merging network to sort this and so on. Agreed? Yes? So, after some step, you will find that you have n by 2 sorted sequence, n by 2 sorted sequence, and you use a merging sorting network of size n by 2 plus n by 2 to give you a sorted sequence of size n. Yes. So if it is the case, now you tell me what is the number of steps you need and then number of comparators you need. So these are the two things you have to find out. Number of steps you need and number of comparators you need. Here we obtain Tn, Cn. Tn is what? Tn is log n plus 1 and this is n log n plus 1, right? Yes, that we obtained already. Now this strategy, let us first, for simplicity, let us consider one example, then you will realize. Tell me 8 random numbers. One of them you tell. 5? Okay. The next number? 7? Huh? 4? Then? 2? 8. Okay. This is the 8 numbers you have. So use comparators here. Output is 5, 7, 2, 4, 1, 3, 6, 8. Now use five has come, 2 has come here, 7, 4, 1, 6, 3, 8. So 2 and here 5 will come, here 7, 4, 4, 5, here 1, 6, 3, 3, 6, 8, right. Now this one, basically right on this side. What is this? Same 2 has come. This is 3. So you will be getting this sorted. So you can think there is phase 1, phase 2, and this is phase 3. Right? Now, if you have n elements, how many phases will be there? Log n phases. Agreed? Now in the ith phase, we are looking for, in the first phase, you need one comparator This is one comparator, one comparator, one comparator, one. There are n by 2 parts. In log n phase, log nth phase, you need n log n plus 1 comparators and 1 part. Right? Now, I need to find out what happens for the ith phase. Can you tell me in the ith phase how many parts are there? Number of parts? In the ith phase? In the first phase, how many parts? In the second phase? In the ith phase? n upon 2 to the power I. Right? And now in the ith phase, and in a particular part, say kth part or a first part, because they are symmetrically distributed. If you have 3 here, here also you have 3. So I need to find out in one part how many comparators are there. Right? That will solve your problem. In the ith or in each part, how many elements are there? In each part, how many elements are there? Number of elements? 2 to the power I. Very good. If I know this 2 to the power I, what is the number of comparators you need? So the number of comparators C2 to the power I is 2 to the power I into I plus 1. Yes? So in each part you need that many comparators. Agreed? So you need total number of comparators in ith phase is what? So tell me, this part I need 3 comparators. This part I need 3 comparators. What is the total number? This plus this? So tell you, same thing you tell. N upon? Very good. So you have n upon 2 to the power I, 2 to the power I plus 1. That is your Ni plus n upon 2 to the power I. Agreed? So the total number of comparators you need, equals to summation n into I plus n up by 2 to the power I is 1 to log n. Agreed? What is the sum? N log n plus tell me the value of this. This is order n, right? Because this is 1 by n, this becomes 1 n by half, so it is this order n. And this is the, so which I can write order n log square n. So you obtained your cost comparators, number of comparators is order n log square n. Right? Now what is the total number of steps you need? Huh? 2 log n. How did you get? In the ith step, in the first step, first phase, number of step is 1. Nth, log nth phase, number of step is log n plus 1. Ith phase, number of parallel steps is log I plus 1. Yes? So, the total number of steps is equal to summation over I equals to 1 to log n log I plus 1, which is log n plus 1 divided by 2 plus log n. Right, it is not 2 log. So this gives you order log square n. So this is that for margin. This is for sorting.
Ith phase number of step is I plus 1. Actually, log nth phase is log n plus 1.
If I was to substitute I as log n.
Nth phase is I plus 1.
So the cost of sorting network is order n log to the power 4n. Now lower bound of sorting algorithm is order n log n. Here it is n log to the power 4n. So log cube n factors away from the cost of cumulative. connection, right? So who is going where and how many connections you can have, all sorts of problems are there. But here, it is a uniform structure, comparators are uniform in nature, and it's a clean diagram. Okay? Yes, no, here's some problem.
Yes.
But the number of comparators is too many, n log square n. Right? See, while I am here, you observe this part is not being used. When the data has been moved to this phase, these comparators are idle. Now, what my point is that can you do some manipulation or some switching technique so that this can be used for this also? That, you know, the only thing is that you see the structure, this structure says same. This structure and this structure is same. I could have, only this link has to be changed, right? So that if we can manipulate little, whether we can achieve the goal. In that case, the number of comparators will be reduced. And number of comparators, if you can reduce, the cost will be reduced. What you are increasing? See, everything you cannot reduce. You are increasing the complexity of the connection. Right? By using, say, 0, the connection structure is this, the data will be coming from this side, and if it is 1, the data will be coming from this side. So those type of manipulation you have to do. So you have to work using pen and paper, and you see if possible. Can you reduce it by, say, log square factor? Or even if it is a log factor, let us do it. Let us see how it looks. Right. Why? First phase it is 1, so it is I. Okay. He's still thinking about that one. Be happy. Is it okay? Now if it is okay, this is okay, everything is okay. You, right? Yes, it is us. But it's not matching, no? First phase, why it is not matching? But then the original somewhere I made some error. Check that one. Why it is broken. Here I wrote K or K plus 1. Yes, you are not attentive at the time. That should be K. That should be Kn in that case. That is simple. Actually, from 2n to n conversion, here only you have to make that see. You have to see that. It should be Kn. Okay? So make the correction from the conversion P2n to Tn. There it should be Kn instead of Kn plus 1. So you can consider this as your one of the term paper problem, that can you use less number of comparators to have this odd even merging networks. Huh? You can define your comparators also. It's not that you define. Now for that you can take the help of the Art of Computer Programming Volume 3 sorting searching by Donald Moore. There is a network for 5 elements, which takes 7 comparisons. Why not 5, 5, 5? So, but you have to do the little study on that, and then you can decide.